Welcome to G Fun Facts Online. Imagine an energy source so vast it could power our entire civilization for millennia. A source that's clean, constant, and located right beneath our feet. This isn't science fiction. It's the promise of deep geothermal energy, the immense thermal reservoir stored in the Earth's core and mantle. For decades, the biggest challenge has been simply reaching it. But a revolutionary technology, born from nuclear fusion research, is about to change everything, potentially unlocking a new era of abundant, clean power for everyone. Let's drill down into the facts. Geothermal energy comes from the natural heat of our planet, generated by the slow radioactive decay of elements in the Earth's core and leftover heat from its formation billions of years ago. For centuries, we've used this energy where it conveniently bubbles to the surface in places like hot springs and geysers. Modern power plants drill into underground pockets of hot water or steam to spin turbines and create electricity. The problem is, these conventional geothermal sites are rare, limited to specific geological hotspots. The real prize, the mother lode of energy, lies much deeper, in what scientists call enhanced geothermal systems and superhot rock geothermal. The sheer scale of this untapped resource is staggering. The U.S. Department of Energy estimates that with new technology, American geothermal capacity could jump from 4 gigawatts today to 90 gigawatts by 2050, with some projections going as high as 300 gigawatts. Globally, the potential is almost beyond comprehension. The International Energy Agency suggests that the full technical potential of next-generation geothermal could meet global electricity demand 140 times over. Think about this. Just 0.1% of the Earth's total heat content could supply all of humanity's energy needs for 2 million years. Beyond being virtually inexhaustible, deep geothermal energy has two massive advantages over other renewables. First, it's a constant baseload power source. It's available 24 hours a day, 7 days a week, regardless of whether the sun is shining or the wind is blowing. This provides the stability our energy grids desperately need. Second, it has a tiny physical footprint, using less than 1% of the land required by a wind or solar farm to produce the same maximum power output. It's reliable, space-efficient, and completely clean. So if this incredible energy source is down there, why haven't we been using it all along? The simple answer is, we've hit a wall. A very hot, very hard wall. The primary obstacle has been the limitation of our drilling technology. Traditional rotary drills, the kind perfected by the oil and gas industry, work by physically grinding through rock with a metal or diamond-tipped bit. This works fine for a few kilometers, but as you go deeper, the conditions become hellish. At depths of 3 to 5 kilometers, temperatures soar past 300 degrees Celsius, or 572 Fahrenheit, and pressures become immense. This extreme heat fries the sensitive electronics in drilling equipment and boils away the special fluids used to cool and lubricate the drill bit. On top of that, the rock you encounter at these depths is crystalline basement rock, like granite and basalt. This stuff is incredibly hard and abrasive. It chews through even the toughest drill bits, forcing drilling operations to a crawl. To replace a single worn-out bit, the entire drill string, which can be kilometers long, has to be pulled out of the hole and then lowered back in. These trips, as they're called, are incredibly time-consuming and expensive. This combination of slow progress, equipment failure, and costly materials means that the price of drilling doesn't just increase with depth, it increases exponentially. Drilling can easily account for more than half the total cost of a geothermal project. The famous Kola Super Deep borehole in Russia serves as a stark reminder of these challenges. It took scientists 20 years to reach a depth of just over 12 kilometers, and they never even reached their target. These physical and economic barriers have effectively capped most geothermal wells at around 2 or 3 kilometers, leaving the most powerful energy source on the planet just out of our reach. But now, a new dawn is breaking. thanks to a technology called millimeter wave drilling. This groundbreaking approach doesn't grind rock, it vaporizes it. The idea originated at MIT's Plasma Science and Fusion Center, where researchers were working on nuclear fusion. The core of the technology is a device called a gyrotron, which generates a powerful, focused beam of millimeter waves. These are a type of electromagnetic energy sitting on the spectrum between microwaves and infrared light. The energy beam is guided down a borehole through a simple metal pipe called a waveguide. When the beam hits the rock at the bottom, it heats it from the inside out, using the same principle as your microwave oven. This intense, localized heating causes the rock to literally melt and turn to vapor in a process called spallation. A stream of inert gas, like nitrogen or argon, is then pumped down the pipe. This gas serves two purposes. First, it cools the rock vapor, causing it to solidify into fine ash-like particles. Second, it flushes these particles back up the borehole and out to the surface. It's an elegant solution. One of the lead researchers, Dr. Paul Waskoff, discovered something crucial during his experiments. Hot, molten rock is incredibly efficient at absorbing millimeter wave energy, far more so than it absorbs energy from high-powered lasers, another technology that has been considered for deep drilling. This makes millimeter wave drilling a more efficient and ultimately more economical path to the Earth's heat. Bringing this revolutionary technology from the lab to the real world is a startup called Quaise Energy, which spun out of MIT in 2018. Quaise's mission is to unlock superhot geothermal energy by drilling deeper than anyone has ever drilled before. Their target is to reach depths of up to 20 kilometers, or about 12.5 miles, where temperatures can reach a blistering 500 degrees Celsius. At these extreme temperatures and pressures, water behaves in a strange and wonderful way. It enters a supercritical state, where it's no longer a liquid or a gas, but something in between, with the properties of both. Supercritical water is an incredible energy carrier. It can hold up to 10 times more energy than the hot water used in conventional geothermal plants. Tapping into this would dramatically boost the power output of a single well, allowing a geothermal plant to generate hundreds of megawatts of power, on par with a large fossil fuel plant. Quaise is developing a hybrid drilling system. They'll use traditional, cost-effective rotary drilling to get through the softer, upper layers of rock. Then, once they hit the hard, crystalline basement rock, they'll switch over to the millimeter wave system to vaporize their way down to the target depth. This hybrid approach offers incredible advantages. First, speed and cost. Millimeter wave drilling is expected to be at least 10 times faster than conventional drilling in hard rock. Quaise aims to complete a 20-kilometer well in about 100 days. And because the cost increases linearly with depth, not exponentially, deep geothermal suddenly becomes economically viable. Second, since it's a non-contact method, there are no drill bits or mechanical parts downhole to wear out. This completely eliminates the need for those costly and time-consuming trips to replace equipment. Third, as the beam vaporizes the rock, it simultaneously melts the walls of the borehole. This creates a smooth, glassy, vitrified lining that seals the well, preventing fluid loss and ensuring stability. This alone could cut operational costs by up to 30%. Perhaps the most brilliant part of Quaise's strategy is their plan to repurpose existing infrastructure. They intend to set up their drilling operations on the sites of old coal and natural gas power plants. They can then use the geothermal steam to power the existing turbines and feed the electricity into the established grid. This approach dramatically accelerates the clean energy transition by reusing valuable assets and skilled workforces. And this is not just a theory. In 2025, Quaise announced a major milestone. At a field site in Texas, they successfully drilled to a depth of 100 meters using their proprietary millimeter wave technology. While that's just a fraction of their ultimate goal, it proved the technology works in real-world conditions And it did so at a speed 10 times faster than any of their previous lab tests. The company is now building a full-scale drilling rig. They plan to have their first 100-megawatt super-hot geothermal system operational by 2026, and their first repowered fossil fuel plant online by 2028. Now, despite this immense promise, there are still hurdles to overcome. Scaling the technology from 100 meters to 20 kilometers is a massive engineering challenge. It requires ensuring the high-power millimeter waves can be transmitted efficiently over such a long distance. Like any new energy project, the upfront costs are high, and securing financing for a brand new technology can be difficult. And there are always concerns about induced seismicity or minor earthquakes, which have been linked to some geothermal projects that use hydraulic fracturing. However, Quaise's closed-loop system, which simply circulates water, may mitigate this risk significantly. Overcoming these challenges will require continued investment, research, and government support to streamline regulations and incentivize development. But the future is incredibly bright and very, very hot. Millimeter wave drilling represents a true paradigm shift. By vaporizing the physical barriers that have held us back, this technology can unlock a clean, reliable, and universally accessible energy source. Deep geothermal can provide the stable, baseload power needed to support intermittent renewables like solar and wind, creating a resilient and truly green energy grid. The implications are profound. It could mean a future where every country can achieve energy independence, powered by the heat right beneath their feet. It could be the key to finally and rapidly transitioning away from fossil fuels. Thanks to the innovators at MIT and companies like Quaise Energy, the prospect of a world powered by the Earth's core is no longer a distant dream. The journey to unlock this El Dorado of clean energy is well underway, and it promises to reshape our world for generations to come.